welcome to the deep dive. Today we're plugging into, well, a really fundamental force, isn't it?
Yeah.
Electricity.
Absolutely fundamental. It powers pretty much everything modern.
Yeah, exactly. And we've gathered a whole load of materials covering, the sources, the effects, circuits, safety, the whole lot.
Right.
Our mission, really, is just to illuminate this essential energy source for you. Make it click.
Yeah, and it's worth taking a second. Just imagine life without it. No lights, no phone buzzing.
Nothing. Just quiet.
Yeah. So this deep dive, it's not just about the technical bits, the volts and amps.
Oh, we'll get into those.
We will. But it's also about appreciating the kind of the elegant science humming away under the surface and why it's just so indispensable.
Okay, so let's start right at the beginning. What actually is electricity? Our sources say a good starting point is static electricity, stuff we all played with.
Oh, yeah, definitely. The classic example, rubbing a balloon on your hair.
Yeah.
What you're doing there is you're actually moving tiny, tiny particles, electrons, between the balloon and your hair.
Okay.
So one thing ends up with like extra electrons, making it negatively charged. The other loses some, becomes positive.
And that's why your hair stands on end, sticks to the balloon.
Exactly that. It's the force between those opposite charges. Attraction.
Right. But that static charge, that's just temporary, isn't it? It's not the kind of continuous power we need for, like, our phones.
No, precisely. That imbalance is temporary. But it leads us nicely to the idea of electric current.
Which is more like a flow.
Think of it, like water flowing in a pipe. Electric current is just the rate, how fast those electrons are flowing past a point in a wire.
Electrons again. So it's all about electrons moving.
Pretty much. For a continuous current, you need those electrons moving in a directed way.
You mentioned free electrons in the materials. What makes some electrons free?
Yeah. That depends on the material itself, how the atoms are structured. In materials we call conductors, metals are the classic example. Some of the electrons in the atoms, the outermost ones, they're held quite loosely.
Sort of easy to knock off.
Kind of, yeah. Imagine them in a sort of outer orbit, easier to escape. So if you apply an electrical force, like a pressure...
Like pressure in the water pipe.
Exactly like that. These free electrons, they start to drift along the conductor. And that drift, that's your electric current.
And insulators?
Insulators are the opposite. Their electrons are held really tightly by the atoms. They don't move easily, so electricity doesn't flow well through them.
Got it. Okay, so we need this electrical pressure or force to get the electrons moving. Where does that come from?
Our sources list quite a few sources.
Yeah, there's several ways. We can generally think of them as primary sources, where we're directly converting some other kind of energy into electrical energy.
Right. First up, dry cells. Batteries, everyone knows these. Remotes, toys, flashlights. How do they work? How do chemicals make electricity? They're clever little things, really. A dry cell uses a chemical reaction. That reaction releases energy and sort of pushes the electrons out.
Okay.
Inside, you typically have a zinc container. That's your negative bit, the negative electrode.
Right.
Then there's a carbon rod in the middle, usually with a brass cap. That's the positive electrode.
Okay.
Around that carbon rod, there's a mix, manganese dioxide, charcoal, often in a little cloth bag.
And the key ingredient?
The electrolyte. It's a moist paste, usually ammonium chloride.
Hang on. Moist paste in a dry cell. That always seemed weird.
Yeah, it sounds like a contradiction, doesn't it? But they're not completely dry. That moisture is crucial.
Why?
Because it allows ions, charged particles, to move between the zinc and the carbon. It's this movement of ions that helps the chemical reactions happen, the ones that generate that electrical push.
But if it dries out, it stops working.
Exactly. Or if the chemicals get used up. No more reaction, no more push, no more electricity.
So in a flashlight, we put the batteries in, flick the switch. What happens then?
When you flick the switch, you complete the circuit. You create that closed loop we talked about.
The path for the electrons.
Right. The chemical reactions inside the cell start generating that electrical push, the voltage. This voltage forces the electrons to flow through the wires into the bulb's filament.
And the filament?
The filament is just a very thin wire that resists the electron flow. This resistance makes it heat up, like a lot.
Until it glows.
Until it glows white hot and gives off light. And often, in torches and things, you use more than one cell connected together.
Yeah, stacked end to end usually.
Right, in series. That basically adds up the push from each cell to get a stronger overall voltage.
Okay, that makes sense for small things. But what about the power for our houses, our cities? Mains electricity, that's a whole different scale.
Oh, absolutely. Maine's electricity is generated in huge power plants, and they use various methods.
Why?
Well, our sources mention hydroelectric using moving water, thermal power burning fuels like coal, gas, or oil to make steam, which spins turbines.
Turbines seem key.
They often are. And there's also atomic or nuclear power, using the heat from splitting uranium atoms, uranium-235 usually, to make steam and, again, spin turbines.
Right, and the electricity we get from the wall socket, it's different from a battery, isn't it? Something called AC.
Spot on. It's alternating current, AC. Unlike DC, direct current from a battery where electrons flow steadily one way.
Like our water pipe analogy.
Exactly. With AC, the electrons wiggle back and forth. They change direction many times a second.
Why do that?
Uh,
Seems more complicated.
It is a bit more complex, but it's much, much more efficient for sending electrical power over long distances.
Well,
Less energy gets lost in the wires.
okay, so how does this AC stuff get from, say, a power plant miles away to my kettle?
It's quite a network, an incredible piece of engineering, really.
Yeah.
So from the power plant, the electricity voltage is massively increased, stepped up using transformers. High voltage means lower current for the same power, which reduces losses.
Okay.
Then it travels along those big high voltage power lines you see stretching across the countryside.
The really tall pylons.
Those ones. They go to substations. There, other transformers step the voltage down to safer levels for towns and neighborhoods.
Safer levels. Right.
Then it travels on local power lines, often on poles, finally reaching your house and entering through the mains board.
Which has the meter and fuses.
Exactly. The meter measures how much you use, and fuses or circuit breakers protect your wiring. Then it's distributed through the wires inside your walls. It's like a huge grid.
Wow. A whole journey. Now, the materials also mentioned electric generators, or dynamos. Where do they fit in?
Generators are really the heart of most large-scale electricity production. They work using a principle discovered by Michael Faraday, electromagnetic induction.
Sounds important.
Hugely important. Faraday figured out that if you move a magnet near a wire or move a wire near a magnet, you can actually create or induce an electric current in the wire.
So turning movement into electricity.
Precisely. Generators basically scale this up. They use mechanical energy from spinning turbines, usually to rotate big coils of wire inside strong magnetic fields. That rotation induces the electric current.
So the steam from burning coal or the water in a dam, it spins a turbine,
Which spins the generator.
which makes the electricity using Faraday's idea.
You got it. That's the core principle for thermal, nuclear, and hydroelectric power.
Okay. What about renewables like solar? Is that different?
Solar is fascinating because it's more direct. Solar cells, or photovoltaic cells, are made from special materials, semiconductors.
Yeah, silicon.
Often silicon, yes. When sunlight hits these materials, the energy in the light, the photons, actually knocks electrons loose within the material,
Creating a current directly.
creating a voltage which can then drive a current if you connect it in a circuit. The brighter the sun, the more electrons get knocked loose, the more electricity you get.
And you can store it.
Yep, often stored in batteries so you have power when the sun isn't shining. You see them everywhere now. Calculators, watches, streetlights, huge solar farms, even spacecraft.
Cool. And wind power. Those big turbines we see.
Similar principle to hydro or thermal in a way, but using wind instead of water or steam.
How so?
The wind has kinetic energy of motion. The big blades catch the wind and start to rotate. That rotation drives a shaft connected to
A generator.
a generator. Exactly. So it converts the wind's kinetic energy into mechanical rotation, then into electrical energy via the generator.
And obviously it depends on the wind blowing.
Absolutely. The faster the wind, the more energy it has, the more electricity you generate. No wind, no power from that turbine.
We also talked about hydroelectric again, specifically dams. How do they work in a bit more detail?
Dams are all about potential energy. Water stored high up behind the dam has energy just because of its height, its position.
Third energy.
Right. When they release the water, letting it flow down through big pipes, penstocks, that potential energy converts into kinetic energy. Fast-moving water.
Okay.
This fast-moving water then hits the blades of turbines, making them spin really fast. And those turbines, again, are connected to generators.
So higher dam, more potential energy. More water flow, more kinetic energy.
Generally, yes. Both factors contribute to how much electricity can be generated. It's a very effective way to generate power, but obviously depends on having suitable rivers and managing water resources.
Now, one point the sources made was that electricity itself isn't really a primary energy source. What does that mean?
That's a really important distinction. Electricity is more like an energy carrier. It's a way to move energy around conveniently.
Oh, yeah.
The primary sources are the raw forms of energy. We find the energy in sunlight, in wind, in moving water, the chemical energy locked up in coal or gas or wood, or even in the atoms used in nuclear power.
So we convert those into electricity.
We convert them into electricity because electricity is incredibly versatile. We can send it easily down wires over long distances.
Right.
And then at the other end, we can easily convert it back into light, heat, motion, sound, whatever we need.
So batteries, then, they're not primary sources either.
No, they're energy storage devices. They store chemical energy and convert it into electrical energy when you connect them in a circuit. Think of them like rechargeable fuel tanks for electricity almost. A battery itself is usually two or more of those cells we talked about earlier connected together.
Okay, that clarifies things.
Yeah.
So we have all these ways to generate electricity. How do we actually make it do stuff? Circuits, right?
Exactly. Circuits are the pathways for electricity to flow and do work. For anything to happen, you need a complete unbroken loop, a closed circuit.
A closed loop. Starting and ending where?
Starting and ending at the terminals of the power source could be a battery, could be the main supply via a plug, and the whole path needs to be made of conductors.
Materials that let electricity flow easily.
Right. So the basic ingredients for a circuit are, number one, an energy source, like a cell or battery, providing that push, that voltage.
Okay.
Number two, conductors, usually metal wires to make the path.
Got it.
And number three, usually a load. Something that uses the electricity, like a light bulb or a motor.
And maybe a switch.
Yeah, a switch is very common. It lets you easily open or close the circuit. Open means there's a break, no flow. Closed means the path is complete, current flows. And you need insulators too, of course, to keep the electricity contained in the wires.
And we draw these using special symbols, circuit diagrams.
Yes, diagrams make it much easier to represent and understand circuits. There are standard symbols for everything: a cell, a battery, a bulb, a switch, wires, even measuring instruments like ammeters for current and voltmeters for voltage.
Our notes mentioned a really simple way to show open versus closed circuits with just a battery, a bulb, and some wire.
Yeah, it's a classic demonstration. You take one wire from, say, the positive terminal of the battery to one contact on the bulb. Then another wire from the other contact on the bulb back to the negative terminal of the battery.
Completing the loop.
Exactly. If you do that, you have a closed circuit, electrons flow, the filament heats up, and the bulb lights.
And if you disconnect one wire,
Instantly, you break the loop. It becomes an open circuit, the flow stops, and the bulb goes out. Simple as that.
what about when a bulb fuses or blows? It's still connected, but it doesn't light up. Why?
Inside the bulb, that little filament wire is very, very thin and delicate.
The bit that glows.
Right. When a bulb fuses, that filament has actually broken, usually because it just got too hot or old. So even though the external wires are connected, there's now a gap inside the bulb itself.
So it's like an open circuit again, just inside the bulb.
Precisely. No complete path for the electrons, no current through the filament, no light.
Okay. So this flow depends heavily on the materials, which brings us back to conductors and insulators. Let's define those clearly.
Sure. Conductors are materials that let electric current flow through them very easily. They don't put up much resistance.
Because of those free electrons.
Exactly. They have lots of electrons that are free to move and carry the charge. Metals are the prime examples. Copper, aluminium, silver, gold, iron. That's why wires are made of metal, usually copper or aluminum.
Any nonmetals conduct?
Some do, yes. Graphite, the stuff in pencil lead, is a conductor. And certain liquids, like tap water, because of dissolved minerals or salt solutions, can conduct because they contain mobile ions. Even the human body conducts electricity reasonably well.
Which is why safety is so critical.
Absolutely critical.
And insulators?
Insulators are the opposite. They strongly resist the flow of electric current. Their electrons are held tightly and don't move easily.
Examples.
Things like rubber, plastic, glass, mica, dry wood, porcelain, and dry air are all good insulators. They're essential for safety, like the plastic coating on wires.
Stops the electricity going where you don't want it.
Exactly. Keeps it on the right path and protects us from shocks.
There was a simple activity described for testing materials, too.
Yeah, you can easily set up a simple circuit with a battery and a bulb, but leave a small gap in the wiring.
Okay.
Then you take the material you want to test, say a plastic ruler, a metal spoon, a rubber band, a key, and use it to bridge that gap.
To complete the circuit.
Right. If the bulb lights up, the material is a conductor because it allowed the current to flow.
And if it stays dark?
Then it's an insulator. It blocked the current. It's a very direct way to see the difference. You could try wood, graphite, different things.
Neat. Okay, so electricity flows through conductors in a circuit. But it doesn't just flow, does it? It has effects. It does things.
That's the whole point, really. As the current flows, especially when it meets resistance, the electrical energy gets converted into other forms of energy.
And our sources mention several key effects.
Yeah, the main ones are the heating effect, the magnetic effect, the chemical effect, and the mechanical effect. Plus, obviously, light and sound, which are often results of these primary effects.
Let's start with heating. That seems pretty common. Toasters, kettles.
Very common. It's probably the most direct conversion. When current flows through a conductor, particularly one with some resistance, the electrical energy turns into heat energy.
The resistance causes heat.
Yes. The more resistance, or the more current, the more heat is generated. And we harness this deliberately in loads of appliances. Electric irons, space heaters, electric kettles, immersion rods for heating water, electric ovens, toasters.
Even light bulbs, the old incandescent ones.
Absolutely. They work because the filament gets so incredibly hot due to electrical resistance that it glows brightly. Most of the energy actually comes off as heat, not light, which is why they're not very efficient.
The sources mention a specific wire, nichrome. Why is that special?
Nichrome. It's an alloy, a mixture of metals, usually nickel and chromium. Its key properties are that it has much higher electrical resistance than copper.
So it gets hotter for the same current.
Exactly. And, crucially, it can handle very high temperatures without melting or degrading quickly. That makes it perfect for the heating elements inside those appliances. Irons, toasters, heaters.
You could even feel it get warm in a simple circuit.
Yeah, if you put a thin piece of nichrome wire in a low-voltage battery circuit, you definitely notice it heating up quite quickly.
Okay, heating effect covered. Next. Magnetic effect. This one feels a bit like magic electricity creating magnetism.
It really is one of the fundamental discoveries in physics. Whenever an electric current flows, it creates a magnetic field around the conductor.
Always.
Always. And we can harness this to make electromagnets.
Wow.
Typically, you wrap insulated wire into a coil, often around a core made of soft iron. When you pass a current through that coil of wire,
The iron becomes a magnet.
instantly,
Yep.
it behaves just like a permanent magnet, attracting iron and steel. But the key thing is, it's temporary.
Only works when the current is on.
Exactly.
Mm.
Turn the current off, the magnetism disappears. This on-off control is incredibly useful.
Where do we use these electromagnets?
All sorts of places. Electric bells use one to make the hammer strike the gong. Electric motors rely heavily on the interaction between electromagnets and other magnetic fields. Big industrial cranes and scrapyards use powerful electromagnets to lift heavy metal objects. Even things like relays and solenoid valves use them.
Fascinating. Okay, third effect. Chemical. How does electricity cause chemical changes?
This usually happens when you pass an electric current through a liquid that can conduct electricity, what we call an electrolyte.
Like the salt water we mentioned.
Yes, or solutions of acids or bases. These liquids contain ions, charged atoms, or molecules. The electric current can force chemical reactions to happen, breaking down compounds or causing new substances to form. The general term is electrolysis.
Breaking down with electricity.
Right. A very common application you might know is electroplating.
Putting a thin metal coating on something?
Exactly. You use the chemical effect to deposit a thin layer of one metal, say silver or chromium or gold, onto another object, maybe made of cheaper metal or plastic. It's used for decoration, like silver-plated cutlery, or for protection, like chromium plating on taps to prevent rust.
Clever. And the last one mentioned was the mechanical effect, creating motion.
Yes, this is really closely related to the magnetic effect. It's the principle behind electric motors.
How does that work?
Remember, current creates a magnetic field. If you place a coil of wire carrying a current within another magnetic field, maybe from a permanent magnet, the two magnetic fields interact. They push and pull on each other,
Making the coil move.
making the coil rotate if it's set up correctly. So you're converting electrical energy directly into rotational mechanical energy into motion.
And motors are everywhere.
Absolutely everywhere. Tiny ones in toys and electric toothbrushes, bigger ones in fans, washing machines, power tools, electric car drive systems, pumps for lifting water. Countless applications rely on this effect.
Amazing how versatile electricity is. Heat, light, magnetism, chemistry, motion. Okay, let's bring it back home. How do we actually measure the electricity we use? Those meters on the side of the house.
Right, the kilowatt-hour meter, or kilowatt meter, its job is to measure the total electrical energy you consume over time.
How does it do that? The old ones had spinning discs, didn't they?
They did. Many still do. Inside, there's basically a small electric motor, sometimes called an armature. The speed at which this motor spins is directly proportional to how much power, current, and voltage is flowing through it at that moment.
So faster spin means more power being used.
Exactly. And the spinning motion is linked through gears to a set of dials or a digital counter. This counter adds up the total energy consumed over time measured in kilowatt hours.
Kilowatt hours. Kilowatt hour. How do we read that, say, from those old dials? To figure out a bill, there was an example.
Yeah, reading the dials takes a bit of practice. You read them usually right to left, noting the lower number if the pointer is between two digits. But the principle is simple subtraction. The example had an initial reading, say at the start of the month, of 4,900,180 kilowatters.
Okay.
And the final reading at the end of the month was 500,625 kilowatters.
So the usage is just the difference.
Just the difference. 500,625 minus 49180 gives 445 kilowatters used during that period.
And the bill is based on that usage multiplied by the price per kilowatt.
That's generally how it works, yes.
I've also heard the term Board of Trade Unit or BOT unit. Is that the same thing?
Yes, exactly the same. A BOT unit is just an older name for 1 kilowatt hour. Kilowatt hour. 1 kilowatt is the amount of energy used if you run a 1,000-watt 1 kilowatt appliance for 1 hour.
Right. And there were formulas mentioned for calculating energy.
Yeah, handy formulas. Energy in kilowatt equals power in watts multiplied by the time in hours, then divide the whole thing by 1,000. Or, since power in watts is also voltage in volts times current in amps, you can say energy in kilowatt equals volts times amps times hours, all divided by 1,000. Useful for estimating appliance consumption.
Now, safety again.
Yeah.
With all this power in our homes, we have fuses and MCBs. Miniature circuit breakers, what do?
They're absolutely vital safety devices. Fuses and MCBs are designed to protect the house wiring and us from excessive current.
Too much current, like from a faulty appliance or plug in too much in.
Exactly. If the current gets too high, it can overheat the wires, potentially causing a fire. Fuses and MCBs act like automatic switches that detect this overload or fault condition.
And they cut the power.
They break the circuit, interrupting the flow of electricity instantly. A traditional fuse has a thin wire inside that literally melts and breaks when the current exceeds its rating. It sacrifices itself.
So you have to replace it.
Right. An MCB is more like a resettable switch. It uses either heat or magnetism caused by the high current to trip a switch open. Once you fix the problem, you can usually just flip the switch back on. Much more convenient.
Definitely. One last thing about home wiring parallel circuits. Why are things wired like that? So you can turn one light on without turning everything on.
That's exactly it. In a parallel circuit, each appliance or light bulb is connected in its own separate branch of the circuit, directly across the main supply lines.
Like separate paths.
Think of it like lanes on a motorway, yes. Each device gets the full mains voltage and it has its own path for the current to flow.
So switching one off doesn't affect the others.
Correct. Or if one bulb blows, the others stay lit because their circuits are still complete. It allows independent operation. If things were wired in series, one after another in a single loop.
Like old Christmas tree lights.
Exactly. If one bulb failed, the whole string went out because the single path was broken. Parallel is much more practical for household wiring.
Makes perfect sense. Okay, we've covered a lot.
Sure.
To wrap up, let's quickly touch on just using electricity safely day to day and maybe conserving it.
Crucial points. Safety first, always. The number one rule our sources stress is never, ever experiment with mains electricity from wall sockets. It's dangerous.
Stick to batteries for experiments.
Absolutely. Low voltage dry cells, properly insulated wires, maybe some insulation tape. Be aware of hazards like damaged cords. Don't overload sockets and keep electricity well away from water. Basic common sense, but vital.
And conservation. It's important, right? More than just saving money.
Definitely. Generating electricity, especially from fossil fuels, has a significant environmental impact. Using less electricity reduces that impact. It cuts down on greenhouse gas emissions and conserves resources.
So we should be mindful.
Yeah, the sources really encourage you, the listener, to just look around your own home. Are lights left on in empty rooms? Are chargers left plugged in constantly? Many devices draw phantom power even when off.
Little bits add up.
They really do. Think about switching to energy-efficient LED bulbs if you haven't already, unplugging things you're not using, choosing energy-efficient appliances when you buy new ones. Every little bit helps conserve energy.
Right then. So, to quickly recap this deep dive, we started with the basics: static charge, electron flow making current.
Then we looked at all the ways we generated dry cells, mains power from hydro, nuclear plants, generators using induction, solar, wind.
And saw electricity as an energy carrier, not a primary source itself.
Right. Then we got into circuits needing a closed loop, conductors, insulators, switches, how diagrams help.
And why fuse bulbs don't work. We looked at conductors like metals and insulators like plastic.
Then the effects heating in irons and kettles, magnetic in motors and bells, chemical in plating, and mechanical in motors again.
How we measure usage with kilowatt meters, calculate bills, and stay safe with fuses and MCBs.
And why parallel circuits are used in homes, plus the importance of safe use and conservation.
It really is a fundamental force woven into everything. Understanding it helps us use it better, safer, more efficiently.
Couldn't agree more. Demystifying it a bit hopefully empowers everyone.
Absolutely. So here's a final thought to leave you with. We rely on electricity more and more, especially with digital tech, AI, electric vehicles. How is this constant evolution changing our relationship with electricity itself?
Good question.
What breakthroughs might be next? Better batteries, wireless power transmission on a large scale, fusion energy. How might those fundamentally reshape things all over again? Something to think about.
Definitely something to think about.
Thanks for taking this deep dive with us.